In this lesson, we're going to look into solving exponential and logarithmic equations. So we've seen that on our calculator, we have base 10 and base e logarithms. So on your calculator, you'll have log, and that's base 10, and then you'll have ln, and that is base e. But what happens when we have a different base? Well, for any logarithm with bases a and b and some numbers m, positive number m that is, if we have a logarithm of a base that we're not familiar with, we can change it into a new base using this formula. Notice the log of the m goes on up top of this fraction, and the log of b goes down here, and we change it to a different base that we're more familiar with. Now, what does that mean for us? Well, what that means is that if we have some log of a base that we're not familiar with or we can't use, then we can change it to a common log like this, the log of m, the number inside, over the log of b. These are common logs, and your calculator can handle this. Or we can use a natural log of m over b. Okay? So in other words, here we have a log. Now, if you think about this, the question here is, what is the exponent you put on 5 to get 125? Well, the exponent you put on 5 to get 125 is 3. This thing should come out to be 3. But we're going to use that change of base formula to find the value of these logarithms, okay? So log base 5 of 125. Well, we can approximate that by going log, common log that is, of 125 over the log of 5. So using Desmos here, we can say log, which is under functions miscellaneous, the log of 125, 25 that is, and then close that, divided by the log of 5, and that is 3. That's what we expected. Again, if we wanted to use natural log of 125, which natural log is going to be used more often. Okay, notice it's the same thing. All right, so again, the change base formula just says we take the log of this is called the argument, over the log of the base, and that's going to give us our answer. Okay, again, this is called the change of base formula. Okay, so now let's come on over here and try this one. Log base 4 of 2. Well, this is the natural log of 2 over the natural log of 4. That's just a cursive ln there is what that is. All right, so let's go try that out. We've got the natural log under miscellaneous natural log of 2, close that parenthesis, divided by the natural log of 4. Okay, and whoops, type the right number in there, 4, and that is 0.5, all right, which is what we expect, 0.5 or a half, because 4 to the 1/2 power, 1/2 power means square root, the square root of 4 is 2, okay, and one more, if we have log base 5 of 0.2, well, that's the same as the natural log of 0.2 all over the natural log of 5. And you can try that out. Natural log of 2 divided by, and that gives us a -1 power. So, oops, did I do it wrong? I did it wrong. So we got 0.2 over 5, and we still get -1. All right, so this is -1. Okay. And one more here. How about the log base 32 of 33? So those ones are all nice, neat numbers that we probably could have come up with just working it out with what we know about logarithms. But what if we have something that's a little stranger? That's a word, I don't know. Like this. Okay, so log base 32 of 33, we're going to change this into the natural log of 33 over the natural log of 32. Okay, so we're going to go natural log of 33 divided by the natural log of 32. And we get 1.0088 or 1.009 would be good enough. All right. Which makes sense because to make 32 the power on 32 to make it 33, it needs to be a little bit bigger than 1 because 32 to the first power is 32. Okay, so that's how the change of base works, okay? So we've seen these properties, okay? We're going to use them a little bit here. So these will show up. We've seen if we have log base b of 1 is 0. So what does that mean for common log? The log of 1, that's base 10, is going to be 0. Or the natural log of 1 is going to be 0. Okay? We saw this property that log base b of b is 1. So what that means is the log base 10, which we don't usually write the 10 there for a common log, is 1. Or the natural log of e, because the invisible base there is e, is 1. We also saw that log base b of b to the x is just x, because x is the power you put on b here, right? X is the exponent. So in other words, if we have log of 10 to the x, well, that's just x. Or if we have the natural log of e to the x, that's just x. Okay. And here again, these cancel each other out. B to the log base b of x. So if these two bases are the same, then they cancel, and we're left with x. So if we have 10 to the log of x, they're both base 10 there. The log is base 10, and the power is base 10. So they cancel each other out. Or if we have e to the natural log of x, those cancel each other out and give us x. All right, so some things that'll show up a little bit here as we go through these, okay? Those are the properties of common logs and natural logs. Which brings us to solving equations here now, all right? The key here, when we're solving these equations, if it's an exponential equation, if we can write it with the same base, then that works pretty nice, all right? Here we have 2 to the 4x minus 2, and so we have 64. So we ask ourselves, is that 2 to some power? And if you go through your powers, it is. It's 2 to the 6th power. So since we can write that as 2 to the 6th power, that means these exponents have to be the same. So 4x minus 2 has to be equal to 6. And now, just looking at the powers there, that is a fairly straightforward equation to solve. Add 2 to both sides and divide by 4. X is 2. That's the key. Here we have 25 to the y equals 625. And so, well, 625 is 25 squared. So we can write it with the same base. So y is 2. That's the idea there. Okay. This is, again, is if we can write it with the same base. Now, here we have 9 to the x plus 3, but this is not a power of 9. But if we think about it, this is a power of 3. And 9 is a power of 3. 9 is 3 squared, right? So we can write this as 3 squared to the x plus 3. Now we have bases of 3. We might rewrite this one more time because power to power multiplies. So this is 3 times x plus 3 equals 3 to the 3rd. And so these two things have to be equal to each of these two exponents. Now that we've written it with the same base, we can say 3 times x plus 3 has to be equal to 3. A whole lot of 3's going on there. Okay, so now maybe distribute here. 3x plus 9 equals 3. Subtract 9 from both sides. All right, divide by 3. And we have negative 2. Okay, so again, if their powers are the same base, we can write them as the same base. and then just make the exponents equal to each other. Now, if that doesn't work, then we're going to need a new method, and this is where our logarithms come in. So solving exponential equations using logarithms. This will be our most general method. Okay, so here's what we want to do. Here's some steps. We've got an equation with an x in the exponent. That makes it exponential. So what we need to do is isolate the exponential. Let's get that 4 out of there. Okay, and we've got 26 on the right and 5 to the x minus plus 1. Okay, now there's lots of ways to think about this, but we're going to try to avoid properties. If you go look online, you'll find a bunch of videos with different properties, but this is the most simple way to go for now here. So now we're going to change this to an equivalent logarithmic equation. Remember, if we have b to the y equal to x, then we can swing that base around, and this means that y is equal to log base b of x. So these two things are interchangeable. That's kind of key property there. Okay, so what we need to do is we need to take our base here, and we're going to swing it around. We're going to write this as a logarithm. So we can say x plus 1 is log base 5 of 26. Well, there we have it. Now we just need to subtract 1. Log base 5 of 26, we don't know that, so I'm going to leave it alone for right now. Okay, so we subtract 1 now, solve. Okay, log base 5 of 26. There is the exact answer. Okay, that is an irrational number. Okay, now, whoops, I forgot my minus 1, huh? Let's get that minus 1 in there. Don't know where that went. Okay, so the 26 is in the log, but the 1 is not. So that's the exact answer. If we want to get an approximate answer, well, we can take log of 26 and divide it by log of 5. And then we'll subtract 1. And this will give us a decimal answer here. Again, this is exact because it's written without rounding decimals off there. But if we go to our calculator again here, log of 26 divided by log of 5. So miscellaneous log of 26, close the parenthesis, whoops, 6 divided by the log of 5. Whoops, I didn't get my divided in there. Close the parenthesis, divided by the log of 5. There it is, 2.024. Okay, so x is approximately 2.024. So that's how it works. We change it to a logarithm, and then we use the change of base. We can find the exact answer, then we can use the change of base if we want an approximate answer. So let's try that same step to find the exact answer of these and then the approximate answer. Okay, so don't change it yet. You want to get that exponential all by itself. That 4 to the x in this case, so divide the 3 off. 4 to the x equals 25. Now we want to change it to a logarithm. Okay, we're using the definition of a logarithm. This is the log base 4 of 25, which we can find out as the natural log of 25 divided by the natural log of 4. And that's the exact answer. We could use a common log too. If we want the decimal, so we'll go log of 25 divided by log of 4. So we got the natural log of 25. And then we're going to divide by the natural log of 4. And there it is. 2.322 is good. Okay. 2.322, so x is approximately 2.322. So again, we have an exact answer here with the logs, and an approximate answer with just the decimals there. What about base e? Well, let's get that e to the 2x all by itself. We've got to get the other stuff out of there. Add 4. So 30 equals 10 e to the 2x. Okay, don't go final log yet. This is 10 times, so let's divide by 10. And so now e to the 2x equals 3. Now we can change it to an exponential form. So let's slide that e over there. That's an e. It looks more like an L. I've got to be careful. There it is. Okay. So this is going to be 2x equals log base e of 3. But we don't like to write log base e that way, right? We want to write it as the natural log. Okay, so we're swinging the base around, and we get the natural log of 3. To finish this off, we're going to divide by 2. Okay, so x is just the natural log of 3 divided by 2. That is the exact answer. Okay, now if we go to our calculator, natural log of 3 divided by 2. Let's try that out. Natural log of 3, close the parenthesis, divided by 2. And we got 0.549, it looks like. Okay, so this is approximately 0.549. Okay. All right, one more here. Bring the calculator on over. Again, we want to get that exponential all by itself, so let's get that 4 out of there first. So 10 to the x plus 1 equals 24. So now we're all ready to change it into exponential, or into logarithmic form. So the exponent, which is x plus 1, equals log base 10, which remember when it's base 10, we don't usually write the base 10, so it's a log of 24. Subtract 1 from both sides. X is log 24 minus 1. By the way, if it's written this way, notice there's no parentheses over here. Well, only the thing that's attached to it is in the logarithm. This is outside. Okay, if you want to put parentheses around here, you can. There's the exact answer. And if we wanted to get a decimal, we can go our calculator. It's just log of, what do we say? Log of 24 minus 1, all right? So log of 24 minus 1. And that gives us 0.380. Okay, so 0.380 is our final answer. 0.380. X is approximately that. All right, so again, the exact has a logarithm in it. In the approximate, it has a decimal. All right, so that's the idea. Again, get the exponential all by itself, then change the exponential function into a log function, and you're good to go from there. Okay, well, what if we have a logarithmic function? Well, we're going to do the exact opposite. Okay, a logarithmic function is an equation that contains a variable in the logarithm. Okay, so first thing we want to do here is we want to get that logarithm all by itself. So we want to get that 3 out of there. That's the first step. And then we'll have log base 4 of x plus 5 equals 6 minus 3 is 3. Now we're going to rewrite this in exponential form. So the x is inside the logarithm. So what we want to do is change it into exponential. And now we have 4 to the third equals x plus 5. And that should be looking fairly reasonable to solve there. So we got 4 to the third. 4 times 4 is 16 times 4 is 64. X plus 5 equals 64. Subtract 5. X equals 59. Okay, now we do have to check this here because the domain of a logarithm, if we have a logarithm, the stuff inside must be greater than 0. You cannot take the log of 0. You cannot take the log of a negative number. So we have to check. Here we got an answer of 59. So the question is does 59, does it work for this problem? So if we plug 59 in, let's try it out here. So we have 3 plus log base 4 of 59. 59 goes in here, it becomes 64, right? So 64 equals 6, and let's just think about it here. So 4 to the third power equals 64. So this is 3 plus the 3 that we had equals 6. All right. That's the ticket there. Okay, 59. Okay. All right. So let's try a couple of these just to kind of wrap this up here. Whoa. Lock that down. All right. So just the reverse of exponentials. We want to get the logarithm all by itself, and then we're going to change it into an exponential. Okay, so get that 3 out of there. So log base 8 of x plus 5 equals negative 1. Now it's time to change it. So 8 to the negative 1 equals x plus 5. All right. So if we subtract 5 there, we get x equals 8 to the negative 1 is 1/8. So we have 1/8 minus 5, which 5 is 48ths. Okay, so this is negative 39/8 when you subtract those. So we get the log by itself, then change it to an exponential. So get that log by itself, get the 5 out of there, that's just being multiplied, so divided by 5. So we got 9, natural log of 3x. Okay, don't try to pull that 3x out of the middle there. You can't touch that 3x there yet. We got to get the log out of there. How do we get the log out of there? We got to, don't divide by it. We have to change it. Remember, there's an invisible base e there. So this is e to the 9th equals 3x. Okay, so we'll just divide by 3 and we're done. So e to the 9th divided by 3 is fine. Okay. Okay, how about this one here? There's an invisible 10 down there, so let's swing it around. So this is 10 to the first, and that has to equal 3x squared minus 2. It's down to a quadratic. Let's add 2 to both sides. 3x squared equals 12. Divide by 3. And we've got an x squared equals 4. And that leaves us with a plus and minus 2. Don't forget your plus and minus. We get plus or minus 2. Okay? Now, remember, we've got to check because we have a domain restriction, kind of like with square roots. Remember, square roots had some numbers that didn't work. They looked like they did, but in the end, they didn't. So let's check. Log of 3 times 2 squared minus 2. So that is 3 times 2 squared. That's 3 times 4. That's 12 minus 2. So that's 10 on the inside. And that does equal 1. Check. Now, if we plug negative 2 in there, well, it's going to square and still become positive. So it works also. Okay, negative 2 is going to give us the same. So we do have 2 answers there. Okay. We didn't check this one, but we should. So if we have 5 times the natural log of 3 times e to the 4th, no, e to the 9th, right? Can't read my own writing. Okay, so here the 3's cancel, and we have 5 times the natural log of e to the 9th. And e to the ninth, natural log of e to the ninth is just going to be 9. So 5 times 9, which is 45. Check. Okay, that's the idea. All right. Well, one application here that's useful to see, okay? We have, a lot of times we're talking about populations. We have what's called an exponential growth function. This is our exponential growth function. A new population is equal to the old population times e to the kt. This looks a bit like our compound interest formula, and which we'll look at here in a moment, okay? So P sub 0 is our initial population, K is the growth rate, and T is the time. All right, so the population in Oregon in 2010 was 3.83 billion, okay? And in 2018, the population was 419 million, okay? So let's find the exponential growth rates, okay, over the 8 years there, all right? So we had 8 years. So let's plug that all in. What we don't know is K. All right, so let's get everything in there except for K. So the new value, P of T there, was 419 million, okay? And so that is equal to the initial population, 3.83 times e to the kt. K we don't know. T is 8. All right, so let's divide by 3.83. And using a calculator, we get 109 there, 109.399. 399, and that equals e to the k8, k times 8. Now let's change this into, it's an exponential form right now, so we need to change it into logarithm form. So swing that base around, and we get the natural log of 109.399 equals k8 times 8. And we'll divide it by 8 to finish that off. And we'll go punch that into our calculator. So the log of that number, the natural log that is, of 109.399, make sure you divide by the close those parentheses, okay? And we got 0.586, it looks like 0.587. Okay, so K is about 0.587. Okay, after you divide this stuff here. All right, so that's exponential growth, okay? And then the last one here where we can use logarithms is, in this case, what if we know we have our compound interest formula that we've seen, and we want to take $200,000 and make it grow into $100,000 at 9% interest rate, okay? So the question is, how long? What will that t value be? So let's plug in the numbers. We want A, which is the new value, 100,000, equals the initial value, 20,000, okay, times 1 plus the rate, which is 0.09, divided by n, and this thing is compound monthly, okay, so that's 12 to the 12t. So we want to figure out how long it's going to take there to go from 20,000 to 100,000, so 5 times bigger. Okay, so let's divide this by 20,000 first, and that's going to give us 5, right? 5 equals 1 plus 0.09 over 12 to the 12t. Okay, now we need to, well, let's go ahead and get that as a decimal. 1 plus 0.09 divided by 12. And that's just 1.0075. So let's change this. It's an exponential function now. We need to change it to a logarithmic function. And so that's going to be our base. So we're going to have log base 1.0075. That feels a little weird, but that works. Of 5 equals 12t. Okay, now we're going to need to divide by 12. So divide by 12. So to do this, we're going to change this into log, or let's go natural log of 5 divided by the natural log of 1.0075. There's our change of base formula. And I got that 12 on the bottom, so maybe I'll just go times 1/12. That's the same as having 12 on the bottom there. And using the calculator, we get an answer of 17.949 or 95. Okay. And that is our time in years. So basically 18 years. Okay. All right. Now that 9% interest is a pretty good rate there. That's what's going on there. So we'll leave it at that. The key again is to, if it's an exponential equation, change it to a logarithm. If it's a logarithmic equation, you're going to change it to an exponential. Good luck.